So again, I just thought we would practice with problems. For each of these things that I throw up, I'm like this one, here's a problem from the book. I'm going to ask you this question that's down in the bottom in bold, as essentially as the clicker question to see, I don't know, to give you practice thinking about how you would deal with a problem so that when the time comes, and it will, you'll be able to. So, this is about a block, two blocks actually. The bottom block with mass capital M is attached to a spring. It oscillates on a frictionless surface connected to, well, this is connected to the spring. The other end of the block of the spring is attached to the wall. And there's another block, a smaller block, I assume, because it looks smaller and they use a small letter M, on top of the first one. It's not attached to the first one, but there is a coefficient of static friction in between the two. So the problem is at some point find the maximum amplitude of oscillation such that the top block will not slip. That's what you're asked to do. I have other questions down here, but what I want to ask you first, how should we think about that thing, finding the maximum amplitude of oscillation such that the top block will not slip?
Question.
Yeah.
Are oscillations included in kinematics?
I would say that oscillations are included in kinematics. That kinematics has, let's just call that X. I'm going to put +5 just for kicks. Oscillations tells you something about X, and therefore you take a derivative and you get something about V. That's V sub X. And you can take another derivative and find something about A sub X. And what you find is that A sub X is, well, I'll write it down. Why not?
Negative.
No, that would be positive.
I mean, no, that's still negative. A omega squared.
A omega squared. Back to the cosine, right? In other words, A of X looks just like X, except it's negative. So when X is small, when X is big and positive, AX is big and negative. And also A, of course, has different units. And so the magnitude of the acceleration A goes from, or the amplitude for the oscillation that A undergoes, that the acceleration undergoes, is capital A times omega squared. So, what should we use from our toolbox?
Well, I guess because the force of
Another 10 or 15 seconds. Think about how you would do this and what you need to know and what's going on, first of all. Last chance. Still answering? No. We're done. Okay. So, someone want to tell me, in your mind, basically what is going on in this problem that you have to, other than, or in your own words, what is going on in this problem that you have to use more than one law for?
Kinematics for amplitude. What you need Newton's second in order to find out where it will still be at equilibrium.
So okay, so that's the two laws. They're the two tools that you want to use. Can somebody else tell me, in kind of common language, what is going on and how you might use one of those tools or both of them? Yeah.
So you can figure out how much you stretch the string, figure out the acceleration of the bottom mass M. Basically M and little M together. And then by seeing how much you accelerate, you use Newton's second law to see how much force needs to be supplied by the friction force in the opposite direction.
Okay, everybody okay with those two? I think both of you were using the same laws in essentially the same way. As pointed out, the maximum acceleration depends on the amplitude, and it depends on the frequency. In fact, it depends on the square of the frequency, because that sits here, omega squared. So the amplitude and the square of the frequency tell you the maximum acceleration that this unit of two objects has as it accelerates back and forth. The frequency you can get because you know the spring constant and you know the two masses that are being oscillated back and forth. And then the statement is, what force is causing this little mass up on top to oscillate back and forth, and that's the static friction force. If it doesn't slip, then the reason it doesn't slip is because the static friction force was big enough to stop it. But there's a maximum static friction force, and so there's a maximum acceleration that little m can have before it slips. And because there's a maximum acceleration, so that's Newton's second law that we're talking about there, there's a maximum acceleration and the acceleration that's needed gets bigger and bigger as the amplitude gets bigger. And so if there's a maximum acceleration that this friction force can supply, then there's a maximum amplitude that will keep that from, that will, beyond which the top one will slip. So this top one will slide back and forth just fine until the amplitude gets big enough that the acceleration, the maximum acceleration, is too big for the friction force to cause. Because that friction force is the only thing causing that little block to accelerate back and forth. It is the horizontal force accelerating that little block back and forth.
Question.
Yeah.
Don't I need to know something about time when I use kinematics? The
equation does not supply anything about the time.
It doesn't supply anything about the time. It tells you that they're connected to a spring. And so you know that the oscillation is going to look like that. In fact, you know a lot about the shape of the curve x of t. You know it's a sine wave. You don't know what time you called t equals 0. So we haven't really fixed a phase angle, but it doesn't matter because the question is largely about the maximum acceleration because the acceleration depends on the amplitude. And so when it asks the maximum amplitude, it's getting at this idea of there's a maximum acceleration that can be supplied by the friction force. So do you use kinematics? I would say you use these ideas in kinematics. You have to know the function of time, something about how the acceleration varies with time.
Wouldn't I need to know exactly when it reaches its maximum in relative time for me to know when the maximum acceleration is reached?
If you needed to plot that, then I would have to tell you more about how we define time. When does it reach its maximum acceleration? It goes back and forth left and right. Okay? When it's all the way to the left, then the x is as small as it's going to get. If this is x of t, then I have implied something. This function right here oscillates around 0. It goes to plus a and minus a. So I've already told you something. I've told you what if I say this is the function, I've already told you what x equals 0 is. X equals 0 is the equilibrium point where the spring isn't stretched. When you push this thing in a distance a and let go, so it'll oscillate back and forth, then where is x? Sorry. When it oscillates all the way over here so that x equals minus a, that tells you how big cosine is right there. It's 1. And it also tells you, because this cosine function is 1, it also tells you the value at that point where you're all the way over here, the value of the acceleration. And when you're all the way over here where where the cosine function is minus 1, so x is not equilibrium, but it's over here to the left at minus a. When the cosine function is minus 1, then the acceleration is positive a omega squared. So when it's all the way over here to the left, a distance a, in other words minus a over here to the left, the acceleration is positive an a omega squared. These equations tell you all of that. It doesn't tell you what time exactly, because I didn't give you a time t equals 0. So I didn't tell you the time scale. But these equations tell you if this is the equilibrium point and this is minus a is all the way over here and plus a is all the way over here, the acceleration is largest when you are farthest from the equilibrium point. In fact, what's the acceleration at the equilibrium point? 0. So
even with the friction force on top.
I'm not sure what you mean by even with the friction force.
So the little block M on top supplies a little bit of a friction force to the opposite direction that it's moving, right? Is that not true?
No, it is true.
Okay.
So
And
what's your? I'm not sure what your point is exactly. Go ahead.
Doesn't that change the point of equilibrium of the system as opposed to off a little bit from the equilibrium of the spring? Because so my thought of that is that the force vector from the mu, the static friction, has to be the same as the spring force in the opposite direction. So it's just off equilibrium.
So let's go back to equilibrium for a second. Suppose this is exactly the equilibrium position, and it's not moving. Then,
Oh, yeah.
and this is the spring stretched or not?
No.
No. So when the spring is in its unstretched position, not pulling or pushing on this thing, then up here, so it's, if I go back to here, if x is 0, then cosine is 0. If cosine is 0, the acceleration is 0. If it's at its equilibrium point, then it's not accelerating. And so little m is not accelerating. And so there's no reason for there to be a friction force because there's no forces, in fact, at all in the horizontal direction. And so this is unlike this oscillator. This oscillator, the equilibrium point depends on how much mass I put on there. And the reason is the force downward is always downward. Whether it's up above the equilibrium point or down below it, the force downward by the Earth is constant, and it's the spring force that's switching back and forth. So that shifts your equilibrium point depending upon the mass that you hung on it. These horizontal things have an equilibrium point where the spring isn't stretched, basically, or where the net force on these objects is 0.
If the mass is big enough, and you consider the table to have friction as well, is there then a region of where?
If the table has friction, if there's friction forces with the table, then what's going to happen as it slides back and forth is, first of all, it's because it's kinetic friction, because it's slipping, you're going to be losing energy into thermal energy all the time. And so what it does is it oscillates back and forth, and then less and less and less. And at some point, it'll probably stop off of equilibrium. I mean, there's no reason that it would stop exactly at equilibrium. At some point, the static friction force and the spring force will cancel, and it will stop somewhere other than its equilibrium point. But that doesn't define a new equilibrium point. It defines a point where it stopped. If you pulled it back and let it go again, it wouldn't suddenly oscillate around that point. It would oscillate around the spring unstretched point.
Okay.
Any questions about that? I think we've gone over it enough to, at what point is the upper mass most likely to slip? I think I already said that at its maximum stretch is where the acceleration is the largest, and that's the most likely place to slip.